So almost everything we've done so far since the beginning of the semester, it's only 3 weeks, has been geometry, learning about vectors in 2 and 3 dimensions, dot and cross products, uh, writing equations of lines parametrically using polar coordinates, lines and planes. And the last class, which was last Wednesday, was on cylinders and quadric surfaces. And today the lecture is on cylindrical and spherical coordinates. So that's all just discussing uh, geometrical objects in 2 and 3 dimensions. And we haven't done any calculus yet. Calculus starts tomorrow. So I remind you, tomorrow for the most of the world is a Thursday, but at CUNY it's Monday. So Monday, we follow a Monday schedule tomorrow. So we have another lecture at 11 o'clock tomorrow morning. And that's when we begin to deal with calculus. So in calculus, you study limits of sequences, limits of functions, continuity of functions, derivatives, integrals. That starts tomorrow. But the last geometrical topic is cylindrical and spherical coordinates. And that's what I'm going to do right now. But if there are any questions about anything we've done previously, I'm happy to start with that. If not, then we go to 16.5 and cylindrical coordinates first and spherical coordinates second. But before we can deal with cylindrical coordinates, I want to review polar coordinates in R2, which is two-dimensional space. So here we have a two-dimensional plane, and you take a point P in the plane, and you want to be able to specify its location. So we've learned two ways to do that. What you do in Calc 1 most of the time is use rectangular coordinates. So from this point, you draw perpendiculars to the x, to the horizontal and vertical axes, call this x and this y, and the rectangular coordinates of this point are x and y. All right, rectangular. This means to locate this point, starting at the origin, you go x units to the right. Of course, if x is negative, that means to the left, and y units up or down, and that brings you to that point. So those are the rectangular coordinates. But there's another way to identify coordinates, which is the following. You can look at the vector or the ray from the origin to the point, and the length of that vector we call r. So the distance from the point P to the origin is r. And you take the angle that the radius vector makes, this vector r makes with the positive x-axis, and you call that theta. So, and you can specify the location of the point just as well with r and theta as with x and y. So how do you use r and theta to locate a point? Well, the r tells you the distance of the point to the origin. So that just means your point lies somewhere on this circle of radius r. So every point whose distance is r from the origin lies on this circle. And how do you specify which point on the circle your point is located at? You take the angle, theta, from the positive x-axis to the ray or the vector from the origin to your point. That specifies the theta. So given r and theta, you can locate the point. So this polar coordinates are r and theta. Those are the polar coordinates. And usually in standard form, you take r to be greater than or equal to 0 and theta to be an angle between 0 and 2 pi. So for example, if you have polar coordinates 2 pi over 3, if those are the polar coordinates of a point, it means you're looking at a point at distance 2 from the origin. So that point lies on the circle of radius 2. And on that circle of radius 2, you take the ray that makes an angle of pi over 3 radians with the positive x-axis. And where that ray intersects the circle, this is your point P. So that point P has polar coordinates 2, comma, pi over 3. Always measure angles in radians. Now, it does make sense to ask about the point with polar coordinates minus 2 pi over 3. So the way you interpret that is you take the ray through the origin that makes an angle of pi over 3 with the positive x-axis. Instead of going 2 units in the positive direction, since you have a minus 2, you go to 2 units in the negative direction. So this point would have coordinates minus 2 pi over 3. So normally one tries to only use a non-negative number for the distance to the origin, but if in a problem or somewhere walking down the street, someone comes up to you and says, here I have a negative value for r, where is this in the plane? This is how you do it. You take the ray through the origin that makes this angle, and you go r units in the positive direction if r is positive, or in the negative direction minus r units in the negative direction. So those are polar coordinates. And cylindrical coordinates are an extension of this, the three-dimensional space. Right? So here you are in three-dimensional space. You have some point P. And again, in rectangular coordinates, if you had this point P, you would drop it the perpendicular to the XY plane. So this is the x-axis. This is the y-axis. This is the z-axis.
Yes, sir.
Yeah.
So, I'm having like trouble visualizing the three-dimensional planes. Even in my homework, it just, I wasn't sure how they got the answers. Like, how do they visualize like a space in a 3D plane? Like 2D is easy to visualize, right? It's just two lines, but
Right. So
um
you're asking about some of the homework in section 13.5?
actually 13.2, because I'm trying to understand this
Right.
stuff.
Okay. 13.2.
So X
All
equals
right.
2 is
Very
one
good.
of the
So,
planes.
so I'm glad you asked that question, but let me, and I'll come back to it. But I start off every class by asking if there's a question about any work we've done previously. So that's really the time you should ask a question like that.
I
Um,
know, I know.
but right now, I'm in the middle of talking about cylindrical coordinates. So when I finish this, there'll be time at the end, and you'll have time to ask all the questions about previous work that you want. Okay? So if you take a point P in three-dimensional space, it has rectangular coordinates. You drop the perpendicular to the XY plane. You have the usual coordinates in the XY plane, plus you have the height Z, that the point is above the XY plane. So this has rectangular coordinates X, Y, and Z. Those are the rectangular coordinates in three-dimensional space. For cylindrical coordinates, you do the same first step. You drop the perpendicular to the XY plane, but you don't take the rectangular coordinates in this point. This is the positive x-axis. This is the positive x-axis. You draw the ray from the origin to your point. This line has a certain distance r, You take the angle from the positive x-axis to this ray, that's a certain angle theta. So in the xy plane, this has points, polar coordinates r theta. Where they say r theta is 0, because it's 0 height above the plane. So r and theta are the polar coordinates of what you get when you project your point into the xy plane. And then this point is a certain distance z above or below this plane. And we say that the cylindrical coordinates of this point P are r, theta, and z. Those are cylindrical coordinates. Okay. So and that's what it is. Those are cylindrical coordinates. You take a point in three-dimensional space, you project it down perpendicularly onto the xy plane. You find the polar coordinates of that point, r theta, in the plane. And then the third coordinate, z, is the height of the point above or below the plane. That gives you the polar coordinates. They're called cylindrical coordinates, for one thing, because there's a very natural way to describe a cylinder in polar coordinates, in cylindrical coordinates. So describe a cylinder. Let's take the simplest cylinder, which is just infinite in both directions, with the center, the z-axis, and every cross-section is a circle of radius a. So if you take any point on this cylinder and you drop it into the xy plane, it'll have polar coordinates. Distance to the origin is a. And the equation of the cylinder in cylindrical coordinates is the cylinder of radius a with the vertical axis, the z-axis. This is just exactly the set of all points r, theta, and z, where r is equal to a, the distance to the z-axis. Theta is any angle between 0 and 2 pi, and z is completely unrestricted. So it's really just all points r, theta, and z where r is equal to a. All you're saying is this is the set of all points where the distance to the z-axis is a, and it can be any height z above and below the plane, and any angle theta with respect to the positive x-axis. That's a cylinder. The easiest thing to describe in cylindrical coordinates are a cylinder. Suppose you had a cylindrical shell. So what does a cylindrical shell look like? You have a cylinder of radius b and an inner cylinder of radius a. And you're looking at the shell. It has a certain thickness. This is a shell of thickness b minus a, right? And how would you describe that cylindrical shell? In cylindrical coordinates, it's all points with cylindrical coordinates r, theta, and z. Theta can be any number from 0 to 2 pi. It's anywhere around the circle. Z can be any number, but r is between a and b. If you were to project this into the XY plane, it would be a ring where the inner diameter, the inner radius is A and the outer radius is B. But then this is just lifted up and down from minus infinity to plus infinity above the z-axis. That's a cylindrical shell. Yeah. Question?
So uh, this is this is the same exact cylinder, but just I guess turned, or is it different? Two different? No,
I don't understand. Same exact cylinder as the cylinder we looked at a moment ago.
no, this one, the one you're viewing, right?
Yeah.
For
So
the
this is,
example.
it's like one cylinder inside another. It's like, think of it as a pipe, right? What is a pipe? A pipe, it's like, it has a certain thickness. There's like the outer circumference of the pipe and the inside of the pipe, right? But the pipe itself has a certain thickness to it. It's not infinitely thin. It's like you have a cylinder and you hollow out another cylinder. That gives you a pipe, just like a pipe. Right? Is that, I mean, is that clear or not?
Well, it's pretty clear, but what I'm asking is, so the hollow cylinders inside the pipe, I guess,
Yeah.
would be like the space, I guess, the distance or something. Uh,
Well, so this is forget the fact that it's three dimensional. Suppose you just cut through this pipe this with a plane. You get something that looks like this. You have an outer circle of radius B, an inner circle of radius A, and you're looking at the ring. When you cut through this pipe or cylindrical shell, you get a ring, has a certain thickness. It's like you have a circle of radius B and you cut out from the center a circle of radius A. So you have all the points whose distance from the origin are between A and B. That's this ring, right?
but here's the thing, so you have A and B, right? So, we're just looking from A to B, the area. This is okay. All right, I got it. All right, thanks.
Right? It's just a ring. But I mean, really, if you ever like pick up a piece of pipe, that's what we're talking about. It has an inner diameter and outer diameter. And the difference is like the actual physical pipe, the piece of lead or whatever that you're holding.
I understand. Okay. Yeah.
All right. What's another example of something that's easy to describe in cylindrical coordinates? So suppose in three-dimensional space, you take a plane or a half plane that hits the z-axis and goes off in some direction. Right? This is a vertical half plane. Now, if this is the positive x-axis, there's a certain angle theta that this vertical half plane makes with the positive x-axis. And in this half plane, there's no restriction on the distance to the origin. There is a restriction on, let's say this is theta 0 is the angle theta. And the height, it can be any height above or below the plane. This is all points whose in polar coordinates where the angle theta is this fixed angle theta naught. Right? So maybe, just to make it concrete, maybe this is pi over 4. It would be like in the xy plane, this is the angle pi over 4 in the xy plane, and you just construct a plane over that in 3 dimensions. It's a plane just coming out of the z-axis. a solid plane, not a solid plane, a complete plane that makes an angle pi over 4 with the positive x-axis. That's a vertical half plane. So again, in cylindrical coordinates, this is easy to describe. Again, this is everything we've been doing so far is geometry, and the hard thing, at least in the beginning, is to learn how to visualize these geometrical objects. And that's just a matter of sitting down for a while in a quiet place or multiple times and looking at pictures and drawing pictures and trying to understand what these things look like. This is a vertical plane. A horizontal plane is even easier to describe in cylindrical coordinates. So if you have a horizontal plane, at height z above the xy plane, in cylindrical coordinates, this is all points r theta, let's say height z naught above the xy plane. All points r theta and z, where z is equal to c naught, z naught. So this height is z naught everywhere. So there's no restriction on r and theta. The only constraint is that the third coordinate of the cylindrical coordinates is this fixed height z naught.
Could I ask another question?
Yeah, of course.
So I don't like the visual part is fine, right? But it's like the vocabulary is a little confusing. Like plane could be anything, like it could be that cylinder as well.
A plane is a two-dimensional flat thing, right?
Two-dimensional, sorry, I didn't get the last part.
Yeah, just a flat two-dimensional object. That's a plane.
So that
It
cylinder,
doesn't have to be one of the coordinate planes. It can be a plane going at some angle, right? Those are planes. And when we study planes, a plane always has an equation of the form ax plus by plus cz equal d in rectangular coordinates. That's a plane where a, b, and c are not all zero. Right? And the way you describe a plane, the way we described the plane so far, is you have a normal vector to the plane n and a point P in the plane. And from the normal vector and the point you can write the plane. So in lesson 4, section 13.5, when we talked about planes, that's what we learned. But I mean, you think of a plane as just, flat, flat thing in space. It can be tilted in any way with respect to the axes. You have the coordinate planes, the XY plane is just that. This is X, this is Y, this is Z. This is the YZ plane. This is the XZ plane. Those are the coordinate planes because they come from the coordinate axes. But any plane going in any angle is a plane. If you take the points 1, 0, 0, 0, 1, 0, 0, 0, 1, on the axes, you could always draw a triangle with those 3 points at the corners. But that triangle is just part of a plane. It can just be extended wherever. There's like the plane that goes through those 3 points. So yeah, I mean, that's a plane. That's lines and planes are like are basic geometrical objects. Here's one which is a little more complicated to describe. It's a cone. So you might have a cone with its vertex at the origin and the axis, the z-axis, and the cone looks like that. So everyone knows what a cone is, and just think of it in three-dimensional space. And if you are at height z above the x-axis, and if this line, this is, let's see, so you would have all points r, theta, and z, where z is equal to a times r. So think of it like this. Suppose at height 1, above the xy plane, you draw a circle of radius a. That's just a circle of radius a above the xy plane. And then you draw the lines from the origin through every point on the circumference of the circle going out to infinity. That traces out a cone. And when you're at height z, this distance is going to be if this is r and this is z, these are similar triangles. So the ratio of r to z, the slope, is equal to a. Sorry. R. Sorry, let me draw a better picture of this. Let me do this differently. So at height, so you have your cone, and you go 1 unit. This is r equal 1. So your distance 1 from the origin, and your height is going to be equal to a. So when you're 1 unit from the origin, your height is a. So this line, the ratio of r to z, this is z equals a. So when r is 2, this is 2a. When r is 3, this is 3a. So the ratio z is equal to ra, or ar. I don't think I'm presenting this as very clearly. So let me. So if you look at the set of all points r theta z, where z equals AR, what does that describe? So theta is unrestricted. So when theta is 0, so you're looking at this in the xz plane, when you're a distance r from the origin, your height z is AR. So it's this point. Yeah. I need to find a better way to describe this. So we have our usual space, and we have a cone. The cone where the vertex is at the origin, and the z-axis is the axis of the cone. And what is the relationship between the distance to the origin and the height above the xy plane? So the way the text describes it is z is some number a times r. So I would think of it, I would prefer to do it differently. But so a is fixed, a positive, and for a fixed positive a, you look at all points r, theta, z, where z is a times r. And this sweeps out a cone. So let's just look at a simple example. Suppose a is equal to 2. So we're looking at all points r, theta, z, where z is 2 times r. Make it z equals a half. So z is a half r. So r is 2z. So as you move, that's really a better way to describe it. But this is the cone. This goes up in a straight line, and you at any point on this line, you take the circle around the z-axis, and that sweeps out a cone. If you learned Maple in Math 155 or 156, it's very easy to graph this. So these are cylindrical coordinates. These will not come up for a long time until we get into integration and we learn how to use these kinds of coordinates to do integrals in three-dimensional space. But that's not anything that we can't do that until we do integrals. Normally, one might wait until one has done the integration before introducing these coordinates, but following the syllabus, this is what we're supposed to be doing today. So we just did. So those are cylindrical coordinates. Let me just repeat it one more time. Cylindrical coordinates. You have a point in space. How do you get its cylindrical coordinates? You project it down into the XY plane. In the XY plane, you have polar coordinates, r and theta. So r theta 0, these are the polar coordinates of this point. Then you have the height of this point above and below the XY plane. So the polar coordinates are r, theta, and z. Those are the polar coordinates of the point. Good. Next, we have spherical coordinates. So cylindrical coordinates are based on a sphere. Spherical coordinates are based on the geometry of a sphere. Cylindrical coordinates are based on cylinders. Spherical coordinates are based on the geometry of a sphere. And so how do you describe a point in spherical coordinates? So it's going to have coordinates rho, which is the distance from P to the origin. That's the origin. So the distance in space is rho, from the origin to the point. Now, this ray makes a certain angle phi with respect to the z-axis. So phi equals the angle between the positive z-axis and the line from O to P. And theta, well, theta is just like the theta in cylindrical coordinates. Theta is sort of like rotation about the z-axis. You take the xz axis, if you rotate it until you hit P, that gives you this angle theta. So the spherical coordinates involve rho, phi, and theta. Those are spherical coordinates. And rho is any number from 0 to infinity. Phi can be any angle from 0 to 2 pi. And theta can be any angle from 0 to 2 pi. So those are the spherical coordinates. And really, it's you have to look at the book to see pictures of what's going on. The pictures I or anyone else can draw by hand are never very good. So what is the relationship between spherical coordinates and rectangular coordinates? Maybe I should also say, what is the relationship between cylindrical coordinates and rectangular coordinates. So if you take a point P, you want to know its rectangular coordinates. You drop the perpendicular to the XY plane. This is X and this is Y. And then you drop the perpendicular to the Z axis. The rectangular coordinates are X, Y, and Z. Rectangular. If this is R and this is theta, the cylindrical coordinates are R, theta, and Z. And the relationship is what? So this is the point X, Y, 0. So R is the square root of X squared plus Y squared. And theta is the arctangent or the inverse tangent of Y over X. And Z equals Z. And if you want to go in the opposite direction, this is what if you know X, Y, and Z, and you want to get R, theta, and Z. If you know R, theta, and Z, then X is equal to R cosine theta. Y is R sine theta. And Z is Z. So these are the transformation rules. This, if you start with X, Y, Z, you get R theta Z. Here, if you start with R theta Z, you get X, Y, Z. So those are the transformation formulas to go from back and forth between rectangular and cylindrical coordinates. Now, what is the same thing? They're the same transformations between going between spherical coordinates and rectangular coordinates. So if you have X, Y, Z, the rectangular coordinates, and rho, phi, theta, the spherical coordinates, what is the relationship between them? Well, rho is simply the distance from the point to the origin. So rho, if this point has coordinates x, y, z, the distance from that point to the origin is the square root of x squared plus y squared plus z squared. If this is the point with coordinates 0, 0, 0, and this point has rectangular coordinates x, y, z, this distance rho is square root of x squared plus y squared plus z squared. Or if you don't like square root signs, rho squared is x squared plus y squared plus z squared. How do you get from the spherical coordinates to the rectangular coordinates? So I have spherical coordinates and I want to get to x, y, z. So this angle is phi. And if I drop this line to the xy plane, this angle is theta. So this is z, the height above the xy plane. If this angle is theta, well, actually I can look at it like this. This is z, this is z. So this is a right triangle. So let me just draw this right triangle slightly differently. This is z. This is phi. This is rho. And Z is rho cosine phi. Right, the cosine of this angle is Z over rho. So Z is rho cosine phi. How do I find X and Y? So this is rho sine phi. This is rho sine phi. So here I have a triangle. Where this is rho sine phi. This is my right angle. This is my angle theta. So this is X and Y. So X, so the cosine of X is X over rho sine phi. So X is equal to rho sine phi cosine theta, and Y is rho sine phi sine theta. Now, I'm never going to ask you to memorize these transformation formulas. If this were to come up on a quiz or an exam, I would give you these formulas. But for solving some problems in vector calculus, you're going to have to know them. So you look them up. But these are spherical coordinates. And just as cylindrical coordinates are useful for describing, among other things, cylinders, spherical coordinates make it very easy to describe a sphere. So to take the most obvious example, suppose you take the sphere of radius A in three-dimensional space. In spherical coordinates, this is all points rho phi theta, where rho is equal to A. It's just all points where the distance to the origin is equal to A for any positive number A. Those are the spherical coordinates. Cylinder, a cone is also easy to write down. Even easier than in spherical coordinates. Suppose we take the cone, and this cone is described by its all points that make an angle phi with the positive z-axis. This is all points rho, or let's say some fixed number phi naught. All points rho phi theta, where phi is equal to this angle phi naught. That is, you take all the points in space where when you draw the straight line to the origin, it makes an angle phi naught with the z-axis. You can rotate that around any way you like. And that's what it is. So that's a cone in spherical coordinates. What about a vertical half plane? So a vertical half plane looks like this. With respect to some angle theta with respect to the positive z-axis, you take this whole half plane, so you take the line from the origin, the ray, that makes an angle theta with the x-axis, and above and below that in all directions forever. That's your half plane. This is all points, say theta 0 is that particular angle. All points rho phi theta, where theta is some fixed angle theta naught. So in some sense, today's lesson is very short because it's just about cylindrical coordinates and spherical coordinates. If you look at section 13.16.5, it also includes integration with respect to these coordinates. But until you get to chapter 16, until we've done integration, we can't do any of that. So the takeaway from today's lesson is simply to know by studying the pictures, and you really need the book because you need to look at the pictures, studying the pictures and drawing some pictures with pen and paper or pencil and paper, just to get an idea of what these coordinates are. And in the process of doing this, you will get a better geometrical feel for three-dimensional shapes, which is something that we need in vector calculus. So that really is all that is covered for us at this time in section 16.5. Okay, so earlier on, someone had a question about vectors, and I'm happy now to answer your questions.
Well, first I was gonna ask, like, I've seen like these cones and figures like on, I don't know, like graphic designers kind of use these to make animation and stuff. So, um, well, the question is like, do they use like distance, or like the computer automatically gives you the
Well,
rate?
so people who have learned this material write the computer programs for designers to use where everything involving cylindrical and spherical coordinates is built into the program. So if the designer says, I want a sphere with center such and such and radius something, it pops up on the screen. So the
That's,
designer doesn't have to know the underlying math, but the people who wrote the computer program did.
so it'd be like if us students, I guess, we were like we're learning this and I guess writing the code. I'm kind of new to like computer science, so I'm just trying to get a picture.
Right. Well, there's really no computer science in this course.
No, I mean, like, obviously the code needs this stuff. That's what you said, sir.
Yes, of course. If you're
Oh,
writing computer programs, if you're writing computer graphics programs, it uses a lot of different coordinate systems.
gotcha. But yeah,
And let me say, writing those programs is a lot harder than learning the material that we're doing right now.
I mean, like pseudocode, like, I would just say put in formula and cone into the program, and I'm done. Like, it's a start, but
Well,
obviously there's probably harder stuff that I don't even.
right. But for this, you need to talk to someone in computer science. And that's
Yeah,
not me.
that's okay.
Right. I'm a math guy, not a computer science guy.
Gotcha. Yeah, but going back to the plane, unless someone else has questions. No. Okay, so y equals 2, or it was x equals 2. It was just like I'm not exactly sure how to like visualize it. Like I'm
I
I'm,
mean,
I'm
if you
starting
just
to
had
get
the
it.
equation x equal 2, what does that look like?
Yeah, yeah.
Okay, well, so it looks differently in 2 dimensions and 3 dimensions. So in 2 dimensions, you're just looking at the XY plane, right? And if you take the vertical line through the point 2 on the XY plane, any point on this line has coordinates 2 comma y. So the graph of x equal 2 in the plane is a line. This line. Those are all the points where in the plane where the x coordinates equal to 2. Okay? Does that make sense? You're just saying find all points where x is 2, y can be anything.
So,
So this is 2, 1. This is 2 minus 1. This is 2 minus 2. This is 2 minus 3. These are all the points where x equals 2. That's the graph of the equation x equal 2.
so, so okay.
Now, in
So
3 dimensions, it's different. What does x equal 2 look like in 3 dimensions? So in 3 dimensions, this is the x-axis. This is the y-axis. This is the z-axis. So in the xy plane, in 3 space, it would just be this line, but z can be anything. So it's like a whole plane. So this is all points where the x coordinate is 2 and y and z can be anything. It's just it's the plane how to draw it. It's the plane cutting through the z-axis at x equal 2 and perpendicular to the x-axis. Right? It's like you have 3-dimensional space and you drop a plane through the point x equal 2. This is 2, 0, 0. It's all the points where the x coordinate is equal to 2. That's what it is. X equal 2 says your first coordinate is equal to 2. Second and third coordinates are completely unrestricted. But x has to equal 2.
so again, like 2D is easy to visualize. It's just a
Well,
straight
2D is
line.
the plane, sure. 3D is hard. 4D is impossible.
What is 4D anyway?
Four
Uh,
dimensions.
meaning like what 3D is like, real life objects. 4D is.
Well, so if you think of in 2 dimensions, every point has 2 coordinates, x, y, or x1, x2 sometimes, right? In 3 dimensions, every point has 3 coordinates, x, y, z, or sometimes x1, x2, x3. So a point in 2 dimensions is just a pair of numbers. A point in 3 dimensions is a triple of numbers. In 4 dimensions, a point has 4 coordinates, whatever they are. In 5 dimensions, a point is a quintuple of numbers.
Just going into physics, I'm assuming. I
No, it's
don't
not.
know.
This is just pure math, simple math. Uh, the number of dimensions is just the number of coordinates. It has nothing to do with physics. So 7, 2 minus 8, 3 is a point in four-dimensional space because it has four coordinates. You want to see what it looks like? You can't. I mean, there's just no picture you can draw, but it's just four numbers. That's right. Every collection of four numbers is a point in four-dimensional space, just like every collection of three numbers is a point in three-dimensional space, and every collection of two numbers is a point in two-dimensional space.
But at least how I visualize the dimensions, right? So 2D is like it's just like a flat, but then 3D is like stretched out, and then 4D is stretched out more, but you can't visualize 4D, right? Um,
Oh, well, I mean,
can you? I don't know.
so, I mean, the definition is precise. A point in four-dimensional space is just a ordered, you just have four numbers in an order, all right? That's the point. That's what it is. You want a picture of it, can't draw it for you. Doesn't mean it doesn't exist because you can't draw a picture. Absolutely not. It's just, it's just what it is. So if you take, for example, linear algebra, which is math 313, this is what you learn about. And it's actually not much that, like in pre-calculus or high school or somewhere, you learn to solve equations like 3x plus 2y equals 6, right? Or you might have a system of equations, right? Or you might have equations in three variables, 3x plus 2y plus 7z equals 6. You want to find all solutions of that. And you could have an equation in four variables, 3x plus 2y plus 7z plus 4w equals 6, right? So you just want to find all numbers that satisfy that equation. So that is all y, x, y, z, w. So you can say if you have a linear equation like this, which isn't much different from what you learned in high school, except there are four variables, uh, a solution of that is a point in four-dimension space. Just like a solution of this, xy, is a point in two-dimensional space, and a solution of this, xyz, is a point in three-dimensional space. So just like asking for solutions of some linear equations in more than three variables. But if you want a picture, I can't give you a picture. I don't think anyone can.
I looked it up. It's the best way I could describe it's like a fan with four sides. It's kind of crazy.
Well, if that helps you, that's fine, but it's okay. Everyone can do whatever they want. It's your
Sir,
imagination is your imagination, or your way of thinking is your way of thinking. So that's fine. But no one can tell you that you must draw a picture of something in four-dimensional space in a certain way. Um, that's you know, if you want to try to visualize it, that's fine, but that's what you have to do. Any other questions? If not, we're actually all done for today because I am really trying to follow the syllabus the way I'm supposed to. Tomorrow we have class, um, and we start lesson 7, which is really the beginning of calculus in chapter 14. Okay. And again, if there are questions, I have problem sessions every Tuesday, Thursday, and Friday. Tuesday and Thursday at 7, Friday at 4:30 in the afternoon. And I certainly encourage you to log on and ask questions about anything in calculus or actually anything in mathematics that you're interested in. Okay. If not, then we are done for the morning. Right. Be well
Thank you,
all.
Professor. Have a good rest of your day.
Thank you. You too. Bye bye.
Have a good day, Professor.